The purpose of this video is to provide an overview of what we will be discussing in our series on chemical equilibrium. We will talk about the learning objectives for the entire series of videos and give you an idea of where equilibrium is important in a real-world situation. So the material for this series comes from Chapter 15 and sections 8.4 through 8.6 in the Trow Chemistry, Structure, and Properties textbook. The learning objectives for this series of videos is that you should be able to describe the relationship between kinetics and equilibrium, determine the expression for equilibrium constant given a chemical equation, use ICE tables to determine equilibrium concentrations given initial reaction conditions or an initial concentration given another initial concentration and the equilibrium concentrations. Given a chemical expression, predict the shift in equilibrium or concentration of the reactants or products based on changes in temperature, pressure, the addition or removal of one or more of the components, and the use of a catalyst. You should be able to convert between Kc and Kp, be able to write out net ionic equations, and given a Ksp value, determine the molar and mass solubilities. Now for this particular set, there are much fewer terms that you will need to concern yourself with. There's the extent of the reaction, the percent yield, equilibrium, equilibrium constant, reaction quotient, Le Chatelier's principle, mass solubility, and molar solubility. So a real-world example of equilibrium that is important, particularly in biological systems, is hemoglobin. Hemoglobin is a protein found in red blood cells that reacts with oxygen, O2. It enhances the amount of oxygen that the body can carry in the bloodstream. It undergoes a binding reaction where your hemoglobin, which we will represent as Hb, can react with oxygen to form a hemoglobin oxygen bound complex. The double-headed arrow that looks like this we will be using throughout this section of videos and for the remainder of the semester, and it's used to describe a process that is in dynamic equilibrium. What we mean by that is that the system will reach an equilibrium between the forward and the reverse reactions. The components will still be interchanging between the reactants and the products, but the concentrations will not be changing. So in our lungs, after a certain point, the concentration of the unbound hemoglobin oxygen and the bound hemoglobin with oxygen, the concentrations of these reach a point at which they no longer change. All the oxygen-bound hemoglobin that you're going to have is bound. Now, the concentrations of the hemoglobin, oxygen, and hemoglobin-bound oxygen are all interdependent. If we were to increase the concentration of O2, oxygen, in the air you are breathing, what you would find is that there would be a greater amount of the oxygen-bound hemoglobin in your blood. However, if you were to reduce the concentration of oxygen that you are breathing, your blood would have a higher concentration of the unbound hemoglobin. This would in fact be suffocation. The relevant amounts of the hemoglobin, oxygen, and hemoglobin oxygen-bound complex at equilibrium are related to each other via a constant called the equilibrium constant. We will be representing this with a capital K. The capital here is important to differentiate it from our rate constants that we were using when we previously talked about reaction rates. A large value of K indicates a high concentration of the products at equilibrium, and conversely, a low concentration of K indicates a higher concentration of reactants at equilibrium. Changing the concentration of any one of the components necessitates the change in the other concentrations in order to restore equilibrium. So if we increase the concentration of oxygen, which would be one of our reactants, the reaction will proceed in such a way to increase the concentration of our products, thus reestablishing the relative amounts of our products versus our reactants. How this works in your body is that in your lungs there is a high concentration of oxygen. This causes the equilibrium to shift to the right. Because in your lungs the oxygen concentration is high, this, in order to establish the equilibrium, which has a relative concentrations, if the oxygen concentration goes up, the oxygen-bound hemoglobin concentration will go up. So the equilibrium shifts to the right, favoring the formation of more and more of our product, the oxygen-bound hemoglobin. So your hemoglobin and oxygen will combine to make more oxygen-bound hemoglobin. In your muscles, there is not a high concentration of oxygen. Because the concentration of your reactant is low, the equilibrium shifts to the left, and so your oxygen-bound hemoglobin starts dumping the oxygen off in your muscles, which enables them to do their biological function. So the equilibrium itself shifts to the right. The hemoglobin-bound oxygen breaks down or disassociates, increasing the amount of free oxygen that is available to your muscles to do their work. Another interesting example is fetal hemoglobin, which we will represent with HbF. The F means fetal, and then the HB retains the hemoglobin like we were using before. So fetal hemoglobin's equilibrium constant is actually larger than that for an adult. Fetal hemoglobin is more efficient at binding oxygen, O2, meaning that the concentration of oxygen-bound hemoglobin for a fetus would be stronger than that for an adult. Because of this larger equilibrium constant, the O2 is actually transferred to the fetal hemoglobin from the mother's hemoglobin in the placenta. So if we look at the top here, this is the mother's hemoglobin. Down here at the bottom is the fetal hemoglobin. Because the equilibrium for the bottom reaction more heavily favors the product, the hemoglobin in the fetus can actually pull the oxygen out of the mother's blood and shuttle it into the oxygen-bound hemoglobin. So what you'll find is when you're pregnant, or if you can get pregnant, that you would find yourself a little bit more winded when you are pregnant because you have more difficulty maintaining oxygenated blood because the fetus is actually stripping the oxygen out of your blood. So how this occurs in the body is you have your fetus here, there is the placenta, and in the placenta there are your fetal veins and your maternal veins, and they interface in the placenta. And so the fetal hemoglobin and the mother's hemoglobin are able to interact. And so the mother's blood interacts with the fetal blood, and because the fetus's hemoglobin is better at binding to oxygen, it will pull the oxygen out of the mother's blood, allowing the fetus to get the oxygen it needs to grow.